What's up, folks? This is Rev Bari, Brown University physics graduate student. Today I bring you the next lecture in classical mechanics. Today we're going to derive Newton's second law in polar coordinates. This is going to be essential for classical mechanics in a gravitational field or in an electromagnetic field. So let's get started. First of all, the motivation. Why do we want Newton's second law in polar coordinates? Well, the reason why is there's a lot of polar things in nature. For example, the orbit of the Earth around the Sun can be analyzed using polar coordinates, right? So here's the Earth, here's the Sun, and the Earth travels around the Sun, maybe not in a circular orbit, right? The orbit itself is elliptical, but we can analyze this geometry using polar coordinates, using circular coordinates, where this distance from the Sun to the Earth is the radial coordinate, and the angular displacement of the Earth can be measured using the theta or phi component, right? And likewise, if we're analyzing an electron orbiting the atom, now of course an electron doesn't have a well-defined orbit, right? There's all of quantum mechanics to tell us that. But if you're considering a classical electromagnetic situation, then you can also apply polar coordinates there, right? So bottom line is there's a lot of reasons to try to test Newton's second law in polar coordinates, right? So first of all, what is Newton's second law in regular coordinates? Well, Newton's second law is simply this: F equals ma, right? Where a is simply the second derivative of the position vector in time. And our goal is to rewrite this second law in polar coordinates. So how do we do that? Well, we're going to focus on a simplifying assumption, which is that we're analyzing central forces. What are central forces? They're simply forces that depend only on a radial coordinate, like gravity or electrostatics. So we're making the assumption that whatever force field we're considering is a function of the radial coordinate and only the radial coordinate. This should be r, the r vector, okay? Where the r vector is the magnitude of the r vector times the unit vector in the radial direction. So what do I mean by this? What is a central force? A central force, I was confused by this for a while, but actually a central force is a very simple idea. For example, here's the Sun, here's the Earth. A central force is a force that depends only on the distance of the Earth from the Sun. It depends only on your radial distance. It does not depend where the Earth is, right? If the Earth is here, it will feel the same gravitational pull from the Sun as it would have if it was 180 degrees on the opposite side. Likewise, the Coulombic force, F is equal to K Q1 Q2 over R squared, is also a central potential force. Why is it a central force? Because it depends only on the radius, only on the distance of the electron from the nucleus, okay? So it depends only on the radial distance of the electron from the nucleus. It does not depend on, for example, any angle like cosine theta or sine theta. And these angles show up when you're considering dipole forces, but when you're considering a Coulombic force, there is no angles involved. It's only a central force. So Coulombic force, gravitational forces, they both involve central force fields, where the force itself depends only on the radius, how far away you are from the Sun or from the nucleus or whatever object you're interested in, and not the angular position of your object. Is the mic still on? Okay, good. So now let's get into the math. So that's the motivation. The math starts with the following. We know that F is equal to ma, so this had better equal mr double dot. Now, what is mr double dot? Well, first thing you need to do is establish the polar coordinate system, and let's figure it out together. So this is x, this is y, and here's a circle. Now, in polar coordinates, this distance is our radial distance. I know you probably can't see that, but nevertheless, that's our radial unit vector. Not unit vector, but radial vector. And this, orthogonal to the radial vector, maybe I'll use phi, or theta, or phi. Let's use phi. So this is the angle vector, right? And it's orthogonal. That means it's perpendicular to the radial vector. All right, great. So let's say this angle right here is phi. So how can I write this r vector in Cartesian coordinates? Well, I can write cosine phi and u sub x hat, where u sub x is the unit vector in the x direction. Okay, this is u sub x hat. and this is u sub y hat. So plus sine phi u sub y hat. Okay, and what about the phi hat vector? Well, since it's orthogonal, what I'm going to do is I'm going to switch cosine and sine and negate the sine. So minus sine phi u sub x plus cosine phi u sub y. Now you might say, why did you do that? It seems like you just memorized it. Not quite, actually. I did that so that when I take the dot product of r and phi, I better get 0 because they're orthogonal, right? And in fact, if I do that, I do get that, right? So I get minus sine phi cosine phi plus sine phi cosine phi, which is manifestly 0, right? So the reason why I knew that phi hat was going to be written like this is simply because I demanded that the dot product of these two orthogonal unit vectors were 0. Okay, great. Now I'm going to take the time derivative of r hat and phi hat so that I can use them to plug into Newton's second law. So let's do that. So r hat, actually let me write it as I usually do. So r hat dot is what? Well, I'm going to have phi dot come out of the chain rule, and I'm going to have minus sine phi u sub x hat plus cosine phi. Oh, this is not a operator or anything. U sub y hat. Okay, wonderful. And this is that. Now notice that minus sine phi plus cosine phi. Does that look familiar? Well, yeah, that's just phi hat. So this is actually equal to, actually, you know what? Instead of calling it phi hat and r hat, maybe it's more consistent if I call it u sub phi, and this is the unit vector in the r direction. So this is the time derivative of the unit vector in the r direction. Okay, very good. So this would be phi dot. Otherwise, it would look weird if I wrote phi dot phi hat. So now I'm going to write phi dot times u sub phi hat. Okay, very good. Now let's take the time derivative of the theta, the angular vector, angular unit vector. So u sub phi hat dot. What is that going to be? So once again, we're going to pull out a phi dot by virtue of the chain rule. Now we're going to have minus cosine phi u sub x hat plus, not plus, minus sine phi u sub y. Okay, now notice if I pull out a negative sign, I have cosine phi plus sine phi. That's simply u sub r. So I'm going to have phi dot u sub r, right? Oh, right, but there's a minus sign. We pulled out a minus sign, so this had better be minus phi dot u sub r hat. Okay, so very good. So that is the time derivatives of u sub r and u sub phi. Now that we have that, let's go ahead and try to figure out what r double dot is going to be. So first thing I'm going to do is take the derivative one more time. Okay, so I'm going to, let's take a look at the r vector here. So the r vector here, if I take its time derivative, then what do I get? Well, I'll use the product rule. So take the time derivative of the first part, leave the second part untouched, and vice versa. Okay, so this is fine. U sub r hat, we already have it right here. Now u sub r dot, what is u sub r dot? Well, we've got it right here. U sub r dot is phi dot u sub phi, right? So that is, let me write that down. So first, let's erase this. R dot times u sub r plus r times u sub r dot. Now u sub r dot is, I remind you, phi dot times u sub phi hat. Very good. So that is r dot. Now I'm going to take the second temporal derivative of r so that I can plug it in over here, right? That's our ultimate goal, remember. So I'm going to have r double dot. R double dot is what? Well, I can either use this expression or this expression. I can derivative either one of them. It doesn't matter. Let's use our most recent expression here. So I'm going to have, let's take the time derivative of r first. So I have r double dot u sub r hat plus r dot u sub r hat dot. Okay, so I've employed the product rule for the first term, giving me two terms. I'll do the same here, but there's three terms here, so I'll get three terms instead of two. So let's do it out. So I'll have r dot, and then I'll have phi dot, and u sub phi, plus r phi double dot u sub phi, and finally plus r phi hat u sub phi dot. right? So very good. So I have 5 terms in total. Now we're going to have to substitute in our previous relationships, right? We figured out that u sub r dot is phi dot u sub phi, and u sub phi dot is negative phi dot u sub r. Okay, so let's see where we have dots in our unit vectors. This one is a dot. U sub r dot, I'm just going to replace that with phi dot. U sub phi. What else? What else has a dot? What else? Okay, u sub phi dot. Now that is minus phi dot u sub r hat, right? Okay, so now let's go ahead and plug and check that in. What's going to happen? Well, let's see. Let's see all of the u sub r vectors. So this is u sub r. This is u sub r. Okay, what's happening here? So I've got r double dot and minus r phi dot squared. Okay, nothing's canceling out yet. Nothing's adding together either. And how about the phi terms? So u sub phi, u sub phi, u sub phi. So I see that I have r dot phi dot, r dot phi dot. Those two terms are going to combine. So let's see where I can write this here. Maybe I can erase this. So r double dot is equal to, so I have r double dot here, r double dot u sub r plus, now r dot phi dot, they add up. So I have 2 r dot phi dot times u sub phi, very good. And then I have r double dot plus r double dot u sub phi. And finally, minus r phi dot squared u sub r. Okay, very good. So this is what we have thus far. Okay, now I'm going to factor out things that have the same unit vector. Okay, so I'm going to factor out the r component vectors and phi component vectors. So let's see what that gives us. Maybe we can simplify something here. So r double dot is equal to u sub r hat. Okay, so I have r double dot minus r phi dot squared plus u sub phi hat, and I have 2 r dot phi dot plus r phi double dot, right? Okay, so very good. So let's erase all of this. No need for any of it anymore. Okay, now I forgot. Nowadays I've been doing so much physics, I forget to make eye contact with the viewers. So if you have any questions or concerns about any of the physics that I've done so far, make sure you put a comment down below and I'll address your concern or question. All right, so very good. So this is r double dot. Now recall, we're dealing with central forces here, right? We made the assumption that the force is only in the radial direction. That means that only this component of the force is going to contribute to the force. Okay, so here's what I mean. We know that F is equal to m r double dot. Now we have calculated m r double dot, and we are going to use only the radial component, only this radial component of r double dot to compute what F is. Okay, so F is going to be m times r double dot, but once again only this radial component of the r double dot vector. So I have r double dot minus r phi dot squared. Okay, so there you go. That right there is our major finding. That is Newton's second law in polar coordinates. But we can actually go a little further than that. Okay, we can exploit what else we found. Now we know that this doesn't correspond to any part of the central force vector, right? So this part has got to be 0. All right, so let's look a little bit more closely at that part. All right, let's look closely at that part. So we have 2r dot phi dot plus r phi double dot equals 0. Now, I'm not the smartest person in the room, but this looks a little bit suspicious. What if I took the time derivative of r phi dot? What would I get? All right, well, product rule tells me I'll get r dot phi dot plus r phi double dot. Now, okay, looks a little similar to what I have here, but maybe not quite. I'm not getting that 2 in. What if I made it r squared phi dot? Let's do the math again. Maybe I can reproduce what I've got here. So then I'd get 2r r dot phi dot. Maybe I'll write my r's as I usually do. Curly r. And then plus r squared phi double dot. Okay, well, let's see what we've got now. We've got 2r r dot phi dot. Okay, so That part is right here. That's the first term. And r squared phi double dot. But here we only have r phi dot, phi double dot. Now, so this is not quite what I want. So maybe I can modify it a little bit by multiplying both sides by 1 over r. Is that going to help me in any way? Well, maybe, because if I divide out by r, then I get 2r dot phi dot plus r phi double dot. And that is exactly what I wanted to reproduce. Now, wait a second, this actually looks pretty familiar. Okay, well, let's take a deeper look at this. So 1 over r d over dt r squared phi dot is equal to this term. But what does that mean? Well, go back to what we had here, right? We know that this entire thing is equal to 0. Okay, so that's telling us that the temporal change in this is 0, right? This whole thing is equal to 0, no? So that means 1 over r, let's write it down here. Okay, this is a big deal. 1 over r d dt of r squared phi dot is equal to 0, right? Let me did I copy everything down correctly? Yes. So what does that mean? Well, take a look at what's inside the parentheses right there. We're being told here is there's something being conserved, some quantity, some physical quantity that corresponds to r squared phi dot that's being conserved. But what physical quantity corresponds to that? Can you think of anything? Well, yes, you can. That right there is the angular momentum. That right there is the angular momentum of a particle, right? Because angular momentum is r cross p, or in other words, r cross mv. And of course, v is omega r, which I can write as m r squared omega, or m r squared theta dot. Or let me use phi, since I've been using phi the entire time here. So this is phi dot. So you can see this is literally the angular momentum, right? Maybe the mass term is missing, but this is essentially the angular momentum which is being conserved in this problem. And that makes sense. Whenever you have a central force, whenever you have a force that does not care about the angular position of a particle, then angular momentum is conserved, right? So that's the big idea here. Now we can go even further. Right, so what we just derived is that the central force for Newton's law works out to be this, right? So Newton's second law in polar coordinates is mr double dot minus this kind of angular term, and that's that, right? So, and let me now prove that energy is conserved using a central force field. So F of r, our central force, right, is equal to this quantity right here. That's what we just proved. R double dot minus r phi dot squared. And don't forget your mass. And let's just distribute out the mass for the sake of it. So minus mr phi dot squared is equal to F of r. And now let me just solve for mr double dot, right? That's the king right there. That's a mass times acceleration. So F of r plus mr phi dot squared is that. And now what I'm going to do might seem a little bit weird, but we're going to do it. I'm going to multiply both sides by r dot. Why am I going to do that? Well, I know in advance that's going to help me derive the conservation of energy. But if I didn't know that, then there's really no way that you could predict that this would be the right step. But regardless, let's do that. Actually, before I do that, maybe I want to do one more thing. I want to express this mr phi dot squared term in terms of something I already know, something that's a constant, and that is the angular momenta. The angular momenta is mvr, or mr squared omega, which is phi dot. So if I square the angular momenta, then I get m squared r to the fourth phi dot squared. But I don't want m squared or r to the fourth, right? So I'm going to divide this by m r cubed. And that's going to cancel out one factor of m and three factors of r, giving me mr phi dot squared as desired. So this right here, this second term can be written as L squared over m r cubed. Okay, so very good. So I've got m r dot r double dot is equal to f of r dot plus L squared over m r cubed times r dot. Now, this term right here, mr r double dot, might not look familiar, but you've known it since kindergarten. This right here is simply the time derivative of the kinetic energy. believe it or not. So actually, you don't have to believe me. Let's take the derivative. So the time derivative of 1/2 mr dot squared is simply 1/2 m 2r dot r double dot. 2 and a half cancel. You're left with m r dot r double dot. And that's exactly what we desired. So okay, so that's pretty good. That's pretty fine. Okay, coming over here, what do we have? Well, this is equal to, now we can say that the force F of r is the derivative, as force always is, the negative gradient of some potential with respect to r, right? So I can say this right here is minus dv dr, and r dot is, of course, dr dt. So really what I have here is negative dv dt, essentially, right? So that's that. And then what do I have here? Well, I've got L squared over mr cubed r dot. So maybe I can make use of that somehow. Maybe I can make that into a temporal derivative as well. What if I said that this is d dt of L squared over mr squared? Would that check out? Let's see. So I've got L squared over m, that's a constant. Now take the time derivative of r to the minus 2. That gives you minus 2 r to the minus 3 r dot, right? So if I do that, I certainly get my r dot as desired, but I get this, and I've got my r cubed as desired, but I've got this unwanted factor of 2. So maybe I need to do L squared over 2mr squared, okay? So that 2, that 1/2 is going to cancel out the 2 and give me what I really want, right? So that seems I've got it in the right time derivative format. So now I can simply write out everything that I've discovered, okay, and show that the energy, the total mechanical energy in a central force field is conserved. So let's, by the way, if you think my derivation is shady or hand wavy, then go look up some other derivation. It's probably not going to have as good of an explanation. So we've got d dt, time derivative of the kinetic energy, d dt. Hopefully you can still see me when I write here. In fact, let me move the camera a little bit. There's no one on the other side anyway. So 1/2 mr dot squared. And this is equal to minus, let's erase all of this. I've got dr cancel, essentially. So I've got minus dv dt, okay? And then plus d dt. Is it really plus, or should this be minus? Maybe I'm making a sign mistake. Well, let's see. So I've got L squared over 2m, L squared over 2m, and I've got r to the minus 2. Take the temporal derivative of this. So I've got negative 2 r to the negative 3 r dot, right? So that is going to give me a negative sign on the front, which I do not want. So actually this should be negative indeed. So that's how geniuses fix their mistakes. So real time, I figured out that this should be a minus sign. So minus d dt of L squared over 2mr squared, not cubed. Taking the time derivative will give you the cube. Okay, so now if I simply, let's see, maybe, am I missing anything? Hopefully not. So now if I just go ahead, bring everything over to the left-hand side, what do I get? Let's bring everything over, okay? So I've got d dt of my kinetic energy term, 1/2 mr dot squared, hopefully you can see all of this, is equal to, maybe I'll revert back to just this board so it looks nicer, is equal to minus d dt of the potential plus L squared over 2mr squared. And now if I simply add this quantity to the left-hand side, then what do I have left over? Let's erase all of this. We don't need any of it. Then all of this becomes d dt of 1/2 mr dot squared plus, okay? Remember there's a minus sign out front for a reason, so that when I add it to the left side, it becomes a plus. L squared over 2mr squared plus v is equal to 0. V of r, of course. And this, ladies and gentlemen, is the total energy of our central force field system. So this total energy is apparently conserved. That's the kinetic energy, 1/2 mr dot squared, plus the potential energy, V of r, plus this angular momentum term, which is extremely important. I cannot overemphasize how critical this angular momentum term is. A lot of people don't give this term enough credit, but it is the reason why the Earth doesn't fall into the sun. And in fact, these two potential terms combined create what is known as an effective potential for our central force field system. So this is the critical final finding for our lecture today. We have just demonstrated that the total energy in a central force field system is conserved, right? dE dt, the change in the total mechanical energy over time, is zero. And that's it for today, folks. Voila, that is the result of today's lecture, and we'll see you in the next one.